Tissue engineering is the use of many different types of cells, all combined to put into constructs or platforms so that we can mimic or create different models for drug testing and to possibly implant.
Using creative, innovative design to improve or replace biological tissue.
At this time, transplant is unfortunately the only curative treatment for end-stage organ failure. In an ideal world, every organ failure patient would be able to receive a new organ. However, there are simply not enough transplantable organs to meet that demand. 22 people die every day waiting for a transplant.
Tissue engineering aims to build new organs to solve this problem. The first attempt to recapitulate biological conditions was using hydrogels for 3D cell culture. Engineers expanded to 3D printing of cells and a process called decellularization, or washing cells from a discarded organ to refill the structure with new cells from the patient. Advances in technology aim to scale up to functional organ engineering.
Tissue engineering has already led to clinical advances. However, so far the tissue-engineered products that have made their way to patients have been limited to thin, relatively avascular tissues.
The classic tissue engineering paradigm involves a cycle of obtaining cells, assembling them into constructs, tuning the external factors and structure for a particular tissue, and creating healthy tissues for future transplantation.
Cells taken from animals or humans provide the starting material for engineered tissues. Tissue engineers gather information about a particular organ and try to design with those parameters in mind.
Tissue engineers began 3D cell culture with synthetic or natural scaffold. More recent systems include scaffold-free culture of cells in 3D and allowing the cells themselves to assemble and cluster. Researchers build systems for providing the chemical and biological cues to cells in gradients or patterns that are present in the body, and combine relevant cell types or incorporate stem cells to build tissues from the bottom up.
Tissue-engineered constructs would then be implanted back into a patient. In addition to implants, applications for engineered tissues include drug testing, studying stem cells and developmental biology, or providing vehicles for injecting drugs or cell therapies. While tissue engineering has already successfully impacted human health, the classic paradigm still has some limitations. To investigate further, we'll focus on two complex organs with dire organ shortage needs. The heart is a highly organized, well-vascularized organ that performs a mechanical pump action orchestrated by electrical signaling. The liver is an intricately structured organ that performs over 500 functions and has many vessels in a sewer-like bile duct system. As previously mentioned, products that made it to the clinic are thin and avascular due to easier design. However, groups are now working on incorporating blood vessels to make thicker engineered tissues. Other aspects of physiology could result in more accurate biomimicry. Each organ has inherent nervous, lymphatic, and immune systems that engineers can hijack in the future to enhance the outcome of engineered tissues. Overall, tissue engineering has so far been and will continue to be one of the most influential fields in human health.